Hi everyone, I'm Andrea Angella, and today we are going to look at a paper on advanced theory for the A2 level computing. The paper is May-June 2017. So let's have a look at it. Okay, so we have the first question. It's we have a user-defined data type that is defining a library book record type that contains an ISBN as an integer and a title that is a string. So the first question that is asked is to write some pseudocode to actually declare a variable called book of type library book record. So here what is actually tested is how you know the syntax of the pseudocode. So let's write what the answer is. So the way to declare a type is using the declare, and then you define the variable name followed by a semicolon and then the type, library book record. So that's how you actually you declare a variable called book of type library book record. So the next thing, the task is to assign the title of the book to Dune. And to do this, you need to use the dot notation. So you do book dot the name of the field that you want to actually assign, and then you need to use the left arrow to do the assignment, and then provide the actual variable, the actual value that you want to assign. There we go. So this is the syntax for assignment in using pseudocode. Then next, you are asked to actually add two additional fields to the library book record type. One is for the genre that has two values, a fiction and a non-fiction. So that means that is an enumerator. And then you have a number of longs that is basically an array of integers ranging from 1 to 99. So what you need to do is to basically copy the type. I wonder if I can actually copy here with this tool. Let's try. No, probably don't. So let's actually type it. So you need to kind of type the same two fields. Then you have the declare ISBN type integer. Then you have title of type string, and this is actually the same as the data type that you already had. You need to add two new types. The first one is genre, and the way to define to declare an enumerator is using the brackets, and you press the values, the possible values that you can have, fiction and non-fiction. And then you need to declare an array, or number of longs, and a different syntax. You can just do like 1.99 to say that this is an array of 1 to 99 elements, or you could actually be more precise and say actually this is an array of 1 to 99 of type integer. And then you need to, don't forget to end the type. Okay, so this is actually the definition of this new type with the two new fields. Then the next exercise is basically testing your knowledge about pointers. You have various identifiers, one pointer to an integer, and three variables, int var and temp1 and temp2, that are all three integers. You have four operations here, and some description here to help you understand what a particular statement means. And you are told that this fourth statement has been executed, and you have a diagram that shows the content of the memory after you executed these four statements. So let's zoom out a bit. So this is actually the content of the memory after the fourth statement has been executed. Okay. And this fourth statement has been added here just for you to understand what they mean. So the first statement is assigning a value to a variable. Very simple. The second statement is assigning the address of a variable to another variable. So the @ symbol basically get the address of a particular variable. So bear in mind, not the value of the variable, but the address of the variable. The third statement is actually getting the value pointed by a particular pointer and then assigning it to another variable, in this case temp2. And the last statement is taking the value of a variable and then assigning to the location pointed by the int pointer. Okay? So let's have a look at the questions. So first of all, you need to say the address of temp2 variable. So you can easily see here, this is the temp2 variable, and this is the temp2 variable, and then the address is, so this is temp2 variable, is basically 6715, as you can see. So if you see this diagram, the second column is basically the memory address and the contents of the variable. So the answer here is pretty much 6715 is the address of temp2, while the content of temp2 is 57. Okay, so watch out for this difference. So int pointer instead is asking for the value of the int pointer variable, and the value of the int pointer is this one, 8216. So 8216 is the answer. 82. Oops. Let's take the tab right there. 8216. Why is not typing? It's not quite typing at the moment. Okay, 8216. There we go. So this is the content of the pointer. So the interesting thing is that obviously the content of a variable of type pointer is actually an address, but this is the value of the pointer. All right. So what actually is the value of the variable pointed by integer pointers? So the way to do that, you need to look at what is the address inside the integer pointer. Is 8216, and let's move to the 8216 location in memory and have a look at the value here, 88. So 88 is actually the value. So 88 is the answer. Okay. Well, the last question is checking that an expression is true or false. So we know that the value of temp2 is 57. You can see that temp2 here, the value is 57. And we know that the value of int pointer, the referenced, is 88, as we had before. So 88 is not equal 56 plus 7. So we know that this statement is false. Okay? Awesome. So next, so the next bit is actually asking you to do some operation to basically verify that you understand how you can do assignments using pointers. So the first one is just a normal assignment, assigning the value 22 to a variable temp2. And we already seen before that you can do that using the left arrow, and then assign the value like that. Let me do this like that. Okay. Next is asking you to assign the address of temp1 to int pointer. Okay, so on the left side of the assignment statement, you need to use the pointer. And on the right, you need to do the address, so you need to use the at temp1. Okay, at temp1, you get the address of temp1, and you assign it into int pointer. And last, what you have is copy the value of temp2 into the memory location pointed by int pointer. So this means that on the left side of the statement, you need to use the referencing of the pointer, and on the right, you just need to use temp2 because you want to save the value of temp2. And this is it. This is basically how you do it. And in order to do this, you could just look above here and see basically these 4 possible ways of doing things. So you just need to identify which one of these 4 was the correct one to use in this case. Okay, let's move on to the next question, question number 2. Okay, here we are basically asking question about security. So the first question is asking, what is a standalone piece of malicious software that can replicate itself using a network? And the answer is worms. So worms are particular types of malwares that is basically using the network to replicate itself, so do as much damage as possible across the network. While the second question is use email to attempt to obtain an individual credential data, is what is basically phishing. So phishing consists of basically sending a well-crafted email that looks like a legitimate email that's sent from an authority or some particular website, well-known website or anything like that, but in reality is actually especially crafted in order to steal confidential data. And that's basically this approach is called phishing. And the third question is asking the definition of what a virus, or description of what a virus is. And the virus is basically a particular type of malware. So is okay. It's a malicious software that basically the main approach of a virus is to basically add itself into executable code so that it can replicate itself. It doesn't necessarily spread across the network, but it's spread across the file system in your machine. So it's basically, I would say, malicious software that adds itself into executable code or data, could be also be hidden inside data, to replicate. So that's kind of a virus. There is a lot of overlaps between these terminologies, but for the purpose of the exam, this is kind of the biggest distinction between virus and worms. Worms replicate across the network. Virus basically replicate using adding itself into data or executable code. So what can you do to see two vulnerabilities that the malware can exploit? So why they were able actually to install, to propagate. So the classic main reasons are the operating system not being up to date, for example, OS not being updated. So it's possible that the malicious, the hackers or malicious users that actually wanted to basically do some harm, exploit some bugs in the operating system, and because the system under attack didn't have the latest security fixes, the computer was basically vulnerable. Another classical way of exploiting is basically not having the antivirus up to date. I think this is one of the classic things. It's very important to always keep the antivirus up to date so that the antivirus knows the latest virus and can actually block them. So these are the two main possible source of exploitation, and others could be you could have click on a link that is is a suspicious link that actually might just do some malicious operation, or you might not have run a scan, because if you have an antivirus but you don't do a full scan every so often, or you haven't enabled like an automatic scans, might be another reason. There we go. Then next we have a question about cryptography and confidentiality of information. So let's see. So there is Anna that wants to send an email to Bob, and Bob and Anna have never sent emails to each other before. So Bob and Anna both have public and private keys, so it's using public-private encryption. And Anna, the first step that Anna do to Bob is ask his keys. So the first question is, what key Bob should send? Okay, so obviously Bob should never send the private key to anyone. So the main purpose of having private keys is because they are private. So the obvious answer here is public, because private keys is always known, it's only known by the person that is a way for the person to actually make sure that is the only one who can actually read data, so you should never share your private key to anyone. So Bob shared a public key to Anna so that Anna can actually send information to Bob and make sure that only Bob can actually read them. Okay, so the second question is explain how Anna can be sure that it's Bob who actually sent the key, because anyone could actually, you know, send a public key. How do I know that it's actually Bob that sent the public key? So the way to do that is using a certificate. So Bob registered with created a certificate using a certification authority, and the certificate contains his public key. And then the certificate, and Anna is basically decrypting the certificate, because the certificate is actually signed using the private key of Bob. And if Anna is able to decrypt the certificate using the public key successfully, that means that only Bob was able to send this information, so that Anna can basically know that Bob is actually the right person she wants to communicate with. Let's try to put it in word, like something like Bob send the digital certificate to Anna. Anna tried to decrypt it, if I can spell, decrypt it using Bob public key. And if it is successful, she knows that Bob is the sender, basically, something like that. Okay. So Bob sent his digital certificate to Anna. Anna tried to decrypt it using Bob public key. Anna tried to decrypt it using the Bob public key, and if it's successful, if she can do it successfully, means that Bob was the sender. And so, because the important thing to say is actually, I don't need to say that, but the important thing is the implication here is that the certificate actually contains the public key and all the other information about Bob. So Anna can verify that it's coming from Bob. Okay, so here we have the next question that's asking what actually the various people need to do in order to do the communication. So the first thing is what actually been said in the first part. So request Bob the public key. Then next, what Bob does is actually send the public key to Anne. Public key to Anna. So send the public key. Then what Anna does is try to. Obviously, we assume that Anna, because the next statement here says sends the email, so it means that you need to actually create the email and then sign the, encrypt the email in a way that only Bob can see. So what do you need to do? So Anna encrypt the email using the Bob public key. So only Bob will be able to decrypt this message because he's the only one who owns the private key. So Anne encrypt the email using Bob public key. Right? Then send the emails to Bob, and then how Bob can actually read the email. You need to decrypt it, the email, using his private key. Right? So if you do that, you will get the actual text of the email as it is. So only him can actually read it, even if with the current system, it doesn't necessarily. It can be sure that it's actually coming from Anne. But it's sure that he's the only one who can actually read the content. Okay, if you really want to be sure that Anna is actually the sender, you need to also Anna should also send the signature, her signature, but although it's not tested in this particular paper. So the next question is on testing logic, Boolean logic. So we have a logic circuit. And if we have been asked to actually write the Boolean algebraic expression that corresponds to these circuits. Okay, so let's do it. The way I do it, I start from the output variable, that is x. So what the operation just before x, the logical gate is an AND, and the first input of the AND is actually A. So we know that there will be A, and something. I can use parentheses just to put something, you know, these second bits of circuits. Let's translate it. Done. I do the same operation. So the last bit is OR. So I know there will be a plus, right? And then here we have not B. I'm not quite sure how to do not B here. Let's do like not B like that. And here I know I have B dot C. Okay. So basically, that's basically what we get. So we get first you have not B plus B dot C. Apologize for I not quite know how to do B not. I'm sure there is a way, but I don't want to waste too much time to find it out at the moment. So let's maybe do not like that, if it's not too confusing. Not B. Okay. So A and not B plus B and C. All right. Then we have been asked to actually write the truth table. So you already have the input from ABC, and we want to actually have X. We have some working space. So my recommended way here is actually to put some temporary variable, like, so let's put not B here, and let's also put B dot C here. Oops, it's not really quite visible. Let's put it a bit smaller for C. Let me put it here, let B dot C. And then I want to also have, like, let's put the value here. Let's call it D, and then put it T here. So now not B. What's not B? We have B. Let's actually do not B. Not B. 0 1 0 1 1 0 1 0 0 1 0 1 1 0 and 1 0. Right? Then I've got B and C. So let's just do B and C. That is 0 0 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. And then D is basically the sum of these two. So 1 plus 0 is 1, 1 plus 0 is 1. Oops. 1, 0 plus 0 is 0, 0 or 1 is 0, 1 or 0 is 0, 1 or 0 is 0. You just need to be careful when you do this operation. No, 0 and or 0 and 0. No, sorry, this one is 1 actually, because it's a HOR. This is 1. I'm doing wrong, so we need to be careful when you do it. Oops. 1. This is 1 because it's a HOR, it's not a hand, so be careful. 1. Okay, so 1 1 0 1 1 1 0 1. Okay, and finally the last step is doing the AND between A and D, right? So you can do the AND between A and D. That is 0 and D is 0, 0 and D and 1 is 0, 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, and 1 and 1 is 1. And you've got the answer here, right? That is 0, 0, 0, 0, 1, 1, 0, 1. Now you've been asked to put these answers into a Carnot map. And the way to do it is fairly simple. You need to see where are the values where 1 is set. So in this case, the first one we have here in the X is when A, B, C are 1, 0, 0. So you start from the top, 1, 0, and then 0. You put the 1 here. Then the next one is this one, when ABC is 1, 0, 1. So you know it's 1, 0, 1 here. And the last one is when all A, B, and C are 1, and you just put it here, 1. Then all the rest is 0. This is 0, this is 0, this is 0, this is 0, and this is 0. Okay? So this is actually the Carnot map. So now you need to loop groups to produce an optimal sum of products. So you need to find adjacent ones in that are in groups of 1, 2, 4, 8, multiple of 2. So you can see here that let me try to find out a tool to do the grouping. So we have 2 consecutive ones here, because we can't do actually 4, and we need to do basically the highest number of adjacent ones you can do. Like we could have done like 1 and 1 isolated, but that wouldn't be the optimal solution. It need to be the biggest set of ones together. And the other one is are these 2 here. So we have two groups that covers the entire map. And all the others are 0, so we don't care about zeros. We want to groups all ones. So this is actually how to do the grouping. And remember that you can actually go off the map and go to the other side. If you had a 1 here, you could have connected this one to that one as well. Or in this case, you didn't need it, but just bear in mind. Then we want to write the actual simplified expression. To do that, you need to basically, let me type here. So we need to go, let's group by group. Let's see the first group, the vertical one. So you need to see where the variables are stable in that group. So A is 1. So this means I want A not negated, while I want B negated. So I want to do A and not B. And C instead is varying. It's varying between 0 and 1 inside the group, so I don't want to consider it because it's always varying. So you only consider the variables that are stable in the group. Then you want to do plus, and then you do the other group. The other group, the horizontal one, the stable variables are A, always stay 1, so we definitely want A. Oops. We always want A. B is switching between 1 and 0 if you move inside the group, so we don't want B. And C if it stays to 1 when we move inside the group. So, and this is actually the simplified expression that that we get. Okay. Then the next things is, so we have a Boolean identity that is given to us, that we know is true because it's given to us, A plus A not A dot B equals A plus B. And we want to simplify the expression that we come up in part C3 using this this operation, this identity. How we can do that? Right, so let me copy these bits here into here. So let's start from the expression that we have, x equals this. Okay. So we, sorry, no, that's not the right one. In part C3, sorry, not this one. We want C3, the original expression we want, right? Because the one we found from the Carnot map is already optimized. So we want to get the unoptimized expression first, and we want to actually come up with the Carnot map using this identity instead of using the Carnot. Okay, so we have this expression. So how can we use this identity? So the way to do that, you need to basically identify a portion of this expression in a way that you can apply the identity. So here you can see that we have not B plus B dot C. It really looks like the left-hand side of this Boolean identity. The only difference that basically we have C instead of B, and we have B instead of A, but in the opposite way. So that's where here we have A, here we have not B, and where here we have not A, here we have B. But they are actually one the negation of the other. So you can actually do this basically. Kind of let's put it here for purpose of explaining. So basically, it's we are replacing in our identity A is basically not B, and B is C. Okay, just put in here just for scribbling. It doesn't need to be here. Let's put here just for making sure that it's not part of this the answer. So now we can just apply. A and will remain. So instead of using the left side of the identity, we use the right hand side, that is A plus B. For us, A is not B. and B is actually C. So basically, this is the simplified expression. And then we can actually use the distributed property and do A and not B plus A and C. And actually, we get the same result that we got using the Carnot maps. Awesome. Next question, number 4. We have a bank has 95,000 customers, and each customer has a unique ID. We need to basically create an ATM machine, a software for an ATM machine, and we have a file that stores a customer ID that is 6-digit numbers between 100,999, an encrypted PIN, and the current balance. And the file can store 100,000 records. All right. So give a reason why a random organization would be the appropriate solution for this file. The main reason is because we are basically when the customer is using the ATM, we know the customer. We want to actually collect the information from the file, the record from the file specifically to that particular customer as quickly as possible. So we want to be as quick as possible. The main reason is actually speed. Basically, we want a quick access, I would say. We want a very quick access to the record. And the algorithms used in order to do that is basically taking the customer ID and creating an hash that is doing the modular operation to 100,000 in order to get the record key. And the record key is actually used in order to add a record in the file to a particular position. So we have been asked to provide the record key given a particular customer ID, and this is just pure plain math. You need to take the number and do the module operation. So let's say 700,004 module 100,000 is just 4 left. And then you can do the same for that one. So 689,998. The rest of the operation is 998. 89998, and the rest of this operation is 2139. Okay, pure math. And what's the possible range of values? The codomain of the function or the hash function. We know that we do the modular operation to 100,000, and we know with math that the value could be 0 if the number is a multiple of 100,000, or the maximum rest you can get is basically 99999. Okay, you can never get 100,000, otherwise you could get 0. And this is actually the range of values that you can get, the minimum value and the maximum value for the record key. Awesome. Now you have a piece of code using pseudocode, and we are asked to complete it. So what this code does is a procedure to insert a new record in the file. Given a customer ID, we have a function called insert record that takes a customer ID as an integer, and we want to actually add the record. Okay, the first operation we can see is actually doing the modular operation to get the record key. We set success to false, so that implies that we repeat the operation until success is true, and then we end. So we only complete this operation when we actually inserted the record. So why we need the loop, we'll now find out. The reason is because we are, even if we use a random access to a file, it's still possible that we get collisions, so that customer with the same customer ID basically are two customers with the same ID will get the same record key. So it's possible that if you try to add those two customers in the file, you will get collisions. And that means that it's possible that the second time you try to add a customer with the same record key, you might find that the record is not empty. So the techniques usually used in this case is to actually iterate, so move to the next records until you find an empty one. And usually there are very little collisions, and so the performance is not too bad, right? It's not just a direct access. Sometimes you need to do a bit of a linear search before actually finding the value, but it's very minimal. So this is actually what this code is trying to do. So if the record at the position record key is empty, because you can see that here when success is true, so if it's empty, it means that we can actually insert the new record, and success is true, done. If it's not empty, we need to basically increment the record key to 1. The problem with the record key is that record key, we need to make sure that if we go above 100,000, we need to come back to the position 0. So we need to make sure that we kind of do a circular +1. Okay, so we want here, we want to just do a record key +1. But if the record key is currently at the maximum value, 99,999, we want to just set it to 0. Okay. Another possible way of doing this would have been just saying record key +1 and then do the modulo operation 100,000. But it's not the way it's been done in this pseudocode. Okay. And so these are actually the answer to implement these insertion algorithms in the file. Why we have an encrypted version of the PIN in the file? Okay. So the reason is mostly for security, because if someone actually get access to the file, all the pins are encrypted. So the attacker will never know the pins of the customer. So it's actually something very important. So even if the ATM gets compromised, the data will still be will not be accessible, the actual password PIN of the customers. And also this means that when you want to verify the PIN, the ATM doesn't need to send the PIN in plain text across the network, but can actually send the encrypted version of it in the network. So the PIN never actually travel across the network. So let's try to put this in words. And so if the file is compromised, the pins of customers cannot be seen by that's kind of, it's probably good enough, but you can also say, and the pin is never sent across the network. So you can actually say that's actually for security reasons. Explain why it's for security reasons. So if the file is compromised, the pins of customer cannot be seen, and the pin is never sent across the network. That's it. Awesome. So then you're asked basically to write down the algorithms, and so how to verify that the actual PIN is correct. So how to do the login of the customers with the ATM. So the customer ID is read from the card. Then the customer entered the actual PIN, and the customer PIN, we know that need to be encrypted before being sent to the network. So, excuse me, the network is encrypted, so the PIN is encrypted. Then so the next step is the customer record is located. So in order to locate the customer record, you need to actually get the record key. So basically, the customer ID is hashed to get the record key, to calculate the record key. And the customer record is located in the file. Then now in the record file, you can see what's the encrypted PIN, and then you can compare with the PIN that's been sent. So the PIN is checked against the PIN in the file. And then if there's a match, it means that actually the user, the customer actually logged in correctly. So the PIN is correct. So you can see the balance. Okay, so question number 5. We have, some networking questions. We've been asked to define the packet, the router, and the TCP/IP mains. When you have a web browser that's trying to request and display a page on an internet web server. Okay, the packet is basically every piece of information that is sent across the network is split into packets. And these packets are basically sent to and from devices one at a time. And basically, the information sent in the request and in the response are basically data across the network, and all data will be split into packets. So I think that's why explain how each of the following items is used. So how the packet is used. Basically, it's used, I would say, the request and response is broken into packets that are packets. Packets are sent to and from devices one at a time. This is kind of the way. And the router is basically a device that is whose responsibility is actually routing the packets across the internet based on the destination address. So it's finding the right route where the packet should be sent. So it's basically the router transmits packets across the internet and decide the route based on the destination address. Okay, and TCP is basically the protocol, the de facto standard protocol using the internet to do packet switching communication. It's basically, so the TCP is the protocol that sets the rules of the communication on the internet. There we go. So now the question is, we are trying to do some video conferencing and the data is transmitted over the internet using packet switching or circuit switching. So explain, let's say, two problems that could arise if the video conferencing were using packet switching. Okay, so the problem with packet switching that everyone can actually use the network, and there is if there is traffic, the quality of service could be degraded, and so you won't be able to enjoy a video conferencing experience at the best of the best of the quality. So I would say traffic on the internet can degrade traffic on the internet can degrade the quality of the service. Okay? And the other problem is the packets are sent across the network without particular order, and they need to be kind of put together at a destination. So it's possible that the video might be out of order, and the picture and sound might not be in sync, and so the classic annoying interruptions that you might have when you actually watch a video online. You do a video conferencing online, so basically you could be the video is received out of order, picture and sounds out of sync, interruptions. Right, that's kind of the possible problem. So what circuit switching means? That's actually the best way to actually do video conferences. Video switching is basically a way to establish a dedicated communication channel before the communication starts. It's basically a dedicated communication channel established before the communication starts. I would say just let's say it's that consists of this establishing a dedicated communication channel before the communication starts. And then why packet switching is better in this case? We kind of said already, it's basically because the channel is dedicated and is only used for this particular purpose, so for video conferencing. Nobody else will be able to use these circuits while the video conference is transmitted. So this means the quality of service will be constant across during the kind of the video conferences. So basically, the dedicated channel is only used for the video transmission. So you get the constant quality of service. Let's say so it's using the full bandwidth the full bandwidth. The dedicated channel is used only for video transmission, so it's using the full bandwidth yeah, that's it, fine. So basically for the quality. And obviously the other reason is kind of there is no loss of synchronization. So the packets, in this case, the information will basically arrives in order, all the data will arrive in order, so there will be no synchronization problems to overcome. So it's definitely the best way to communicate in this situation. Okay, so question number 6 is asking, so you have a computer system that is managing some function in a vehicle. You have a vehicle with a number of sensors and actuators. So it's basically a sensors monitoring the moisture on the screen, and then you have, if the moisture exceeds a particular value, the windscreen wiper motor turns on automatically. So they've been asked to say what this system, the name of this type of system, and the answer is this is a control system. And the reason is because it's there are actuators. So if you have a system that monitors the environment and also act on the environment so using actuators, you have a control system. While if you only monitoring information, only reading information using sensors from the environment, you have a monitoring system. So in this case, you have a control system because there is also something that act on the environment. In this case, the wiper motor that need to be turned on. So, and the reason is actually because we have actuators. The system uses actuators. Okay. Then it's saying that in order to actually read information from the sensors, it does a loop, and the value read from the sensor is then processed. So what are two drawbacks when you're using this method? So this method is called polling and consists of every so often using a particular period, let's say once every 100 milliseconds, you check that there is a value change in a particular sensor. So the main drawbacks is that the CPU needs to do these checks very frequently. So it's not used for valuable other purposes like running software. So it's basically there's a waste of CPU time checking values even when maybe there is no change, when they don't change, right? So it's possible that the particular value of the sensor is stable, but you still need to actually every so often check it. So you're kind of wasting time. And the other things is that because you need to do a polling every so often, so you need to set a particular period. You could do a check every second, but it's not that frequent enough. You could do checking every 10 seconds. If you have an high period, obviously you waste less CPU time. But if it's too big, as soon as there is a change in a sensor, you need to wait that time in order to actually detect a change. So basically, there is some delay before the system can react to changes in the environment. So you can say something like, so the drawbacks is sensors are not processed immediately. So sensors are not processed immediately. While sometimes in particular systems, it's critical that the system can react to the changes in the environment very quickly. Okay, and that's pretty much it. So the next page is asking, okay, it's showing an alternative method of doing this checking that is actually using the interrupts. So it's showing certain steps. So as soon as there is an interrupt coming in, we disable the interrupt, we set the current task, we identify the source of the interrupt, we jump to interrupt service routine, we restore the task, and we enable the interrupts. Okay, so the idea is that instead of this having the CPU to do the check every so often using polling, the CPU does nothing, and there is some circuitry that detects that this is a sensor in a sensor change, and then notify kind of the CPU that there is a change using the system that consists of interrupts. So as soon as the CPU detects an interrupt, disable every interrupt, so that it can handle the particular sensor. So the first question is why we need to do this disabling of interrupts. Because when the CPU is actually executing the interrupt handler, that is actually the service routine that processes the data that is coming in, we don't want really to interrupt again. We don't want to be able to, in other interrupts, to interrupt the interrupt handling. So it's very important to disable interrupts, and that's also why important is to process interrupts in priority orders, so that interrupts with highest priority go first if they arrive at the same time of other lower priority interrupts. So basically the reason is to basically avoid the interrupt process to be interrupted by other interrupts. And why we want to then re-enable them? Obviously, we want to re-enable them because we want to be able to process other interrupts that might happen in the future. Otherwise, if we do never enable the interrupts, the system will basically be blind, will not be able to detect any additional changes in the environment, so will be pretty much useless. So it's very important, it's critical that the interrupt are re-enabled as soon as the interruption has been handled. So it's basically re-enable interrupts so that can be dealt later. Okay, the next question explains how the current task is saved in step 2. What does it mean saving the current task? So at the moment when the interruption arrived, the CPU was actually executing some particular program. So it also has some state where it was. So we want to be able to resume resume the program that was running at the time of the interrupt as soon as the interrupt has been handled. So in order to do that, we need to save all the registry into the stack so that they can be actually retrieved later. So basically all the content of the registers, so all the registers is pushed on the stack, basically pushed into in memory. And that's basically what happens. And the restore task will actually pop all the registry values from the stack to restore the actual context. Okay. Then, two benefits of using interrupts. So as I said before, one of the problems is kind of is why the polling is ineffective. It's the opposite, right? So the polling is ineffective because it doesn't react immediately to external changes. While using interrupts, as soon as the change is detected, it actually interrupts the CPU. So basically, one of the benefits is react immediately to external value changes. All right, it's definitely a great benefit, and also there is no reason to interrupt the CPU if there is no actual change in the environment. Or, for example, so the sensor is checked only when an interrupt occurs. So yeah, so this basically means that if there is an interrupt, then the CPU goes and asks the sensor to give the data, but it never does that when it doesn't receive an interrupt. So the interrupt is only sent when there is actually a change in the value of sensed. Okay, so we don't waste any load time in order to actually read the data from the sensor. So we only read the data when an interrupt occurs. So that's when actually there is a change in the environment that we care about. The last question is actually setting checking if the bit in position 9. So let me circulate. So this is the bit in position 9. Oops, not with that. Sorry. So let's take that. So bit in position 9, that's this one. So one instruction that does the following. So if the bit 9 is 0, set the accumulator to 0. If it's 1, set the accumulator to a non-zero value. So basically we want to check if the bits in position 9 is 0, 1. All right, that's the way to do it. So all the time you want to check if a particular bit is 1 or 0, you use an AND operation. So let's do it. So you do an AND operation, then you need to put a mask, and the mask need to be all zeros except 1 in the position 9. So the easiest way to do it using like hexadecimal. So the first four bits are 0. Let's use 0. The next 4 bits have 1 in the second least significant bit. So this means this is a 2, and then all the others can be 0. So this basically is a number that contains all zeros and 1 in position 9. And if you do this AND, the end result will be 0 if the first bit, bit 9 is 0. Otherwise, will be basically this number 0200. That will be a non-zero value. That basically satisfies the requirements that's been asked. So having said that, this is actually the end of the paper. And thank you for watching, and hope this has been useful. If you have any questions, just feel free to drop a question in Slack. And thank you very much.